Okay, hello everybody. Can you hear me? Is there any problem about my voice? Okay, I am sorry about last lesson. I had a minor car accident. It was was not big, but I couldn't do the lesson. I am okay, thank you very much. It was not big deal, but I couldn't do the lesson, so we had to do this in today. Yes, I am okay. Thank you very much. Thank you. Okay, let's update the presentation. You can see the presentation, right? I upload it. Okay. In the last class, we discussed the fundamentals of the Boolean algebra, and we discussed some postulates and some rules and some basic theorems. We also saw the proof of these theorems and how to do it from the basic postulates. Let's see them. Also, we saw the truth table. Okay. There was a three gates, not, and or gates. And we also saw the switch equality of these gates. We said that AND gates is like the serial switch, and OR gate is like that parallel switch. So we see the logic expression. Let's see, can we see? We see the logic expression and the circuits expression of the gates. You did this example. Also, I want you to keep the pencil and paper in this lesson because we do some exercise. So you did this, you saw this example, and you see the truth table. What does it mean? You can use the truth table for the circuits, create a logic circuits. Also, you can use the logic circuits to create a truth table. So there was basic theorems. For example, 0 is ineffective for OR gates. Also, 1 is ineffective for AND gates. You know that's theorems. So you saw the proof of these theorems. And there was a De Morgan's theorems. I said that you have to memorize it. Also, you can prove that from this truth table. there was a theorem 5a. Let's see. There is a x or y, and it's equal not x and not y. There's another one in here. Complements is important when you take a complement of some expression. You have to know what does it mean. De Morgan's theorem is important for that, and my recommended you have to memorize this truth table. You have to know that very well. So there was a consensus theorem like De Morgan's theorem. Let's see that one x and y, or not x and z, or y and z equals x and y, or not x and z. And there's another parts of these theorems. Let's prove this one. This expression equals this one. Let's prove that. So you can multiply this parenthesis, right? There's a x. You can let's prove. We prove the first one, not second. I'm sorry. Let's do this. And there was a multiplication like the decimal numbers. It's the same rules in the binary or the Boolean algebra. There was x and y, not x and z, y and z. Let's prove that this expression equal this one. There was a 1 in there, right? We can write the 1 in here because 1 is ineffective for AND gates. Also 0 is ineffective for OR gates. So we can use this expression for the 1 like this. X or not x is equal 1, right? For example, you said x is 0. 0 and 0 or 1 means 1. For example, if you got x 1, 1 or 0 means also 1. So we can multiply this parenthesis also, and we can write like that, right? X and y, x and y and z, this one. So we can set this one also. We can write this. So how can we create this expression from this? You have in parentheses x and y, or x and y and z. How can get this from that one? We can use this. I will try to write, but I'm writing with mouse, so it was not pretty. Sorry about that. We can use x and y parentheses, right? 1 or z, right? This expression is equal this one. And what was the 1 in OR gates? If one of them is 1, it means it's equal 1. Z is ineffective in there because it's not matter Z 0 or 1. It's equal to 1. So in AND gate, we don't use the right one, and we got x and y in here. So the other part is the same. You can use not x and z parentheses, and you get 1 or y. So it's the same rules in here. you can get 1, so it means not x and z. Okay. You see 3 operators, the basic one, not, and, or. They are so important because you create all of gates, all of operators from those 3 gates. And you get parentheses, and you know that this is also kind of operator. You can use parentheses as you like this. So Boolean function, let's say binary variables, binary operators, or and binary and unary. I said in Boolean function, binary means not just 1 and 0, right? It means 2 variables. Not like binary we saw in first week. It means 2, binary. And there's a unary operator, just like not, right? Not gate has a unary operator. There was examples. So there's a truth table. We have, let's see that. We have 3 inputs, x, y, z. So what does it mean? It means we have 8 variables. 2 power of 3 means 8. We have 8 variables, and we have results f1, f2, f3. This is just example. It is not the constant equal. So there's a example about the logic gates. You did this kind of example last week. f2 equals x or not y and z. So there's another one. I used to ask you to do that examples, but I shared the this paper, and you already solve all of these examples, so it's not matter. But please try to do yourself. Try to get F4 without looking at that one. So there is one example. I want you to do that. I edit. I give you 5 minutes, and I ask you to write Q with Boolean algebra, like that. You got F4 from these circuits, and I want you do this one. Please everybody try to get Q. You have AND gate, OR gates too, and NOT gate. Please try to write Q. I give you 5 minutes for that. If you done, please write down in conversion area. Just write the Q. If you finish expression, write it down. I did it. Try to force your memory. Let's see the trick. There was a interconnection in here, A and B and C. There's one interconnection. Let's do another one. There is another interconnection, not B. Yes, Talha. It's right. Correct. Let's see the other ones. Congratulations, Talha Ferah. But not use plus, just use dots for AND gate. Because the multiplication means nothing in the Boolean algebra. We use dots and plus. Plus means OR, dot means AND gate. But you got the true answer. So you know the truth table, right? How many inputs we have in here? We have 3 inputs. So what does it mean? It means we have 8 variables, right? We have 3 inputs and 8 variables. We have interconnections like A, B, C, not B, not C, not B, and or not C. Can you fulfill this table, please? I give you another 5 minutes for that. Please draw this table in the paper and fulfill all of the blank parts. For example, there's a AND gates, right? There's a 3 inputs AND gates. And if there are any zeros in AND gates, so the result means 0. Okay, let's see this Q. Q is the answer of this logic gates. We have AND gates and we have 3 inputs. It means A and B and C. It is interconnection 1. So we have NOT gates and it is also interconnection. We have NOT B and we have NOT C, right? All of them is interconnection. This part is A. This is a short circuit. So we have OR gates and the inputs are NOT B and NOT C. So the result of this OR gates is B or C, like this. And we have another AND case, and the inputs of these AND gates are A, not B or not C. This means A and not B or not C. And we have the last one. Last one is OR gates, and there is a 2 inputs. One input is A and B and C. The other one is A parenthesis B, not B or C. So just OR these 2 expressions, and you got the answer. So let's do the truth table of them. We have AND gate. In AND gate, 0 is effective. If any of them is 0 from the input, so that means the result is 0. It's not important the other 2 is 0 or 1. So we have 0, 0, 0, so it means just 0. We have 0, we have 0, we have 1, 0, 2, 1. It is not important because we have 0, so results it's 0. Also, there is a 0, 0. Sorry about the writing, it's ugly, I know, because I'm trying to write with mouse. I don't have an iPad. So, and 0, the last one is 1, 1, and also 1. We have 1. Not B is simple. Just flip these numbers. Not C also simple. And if you have not B and not C, you can OR both of them and got the results. So you have not B or not C, and also you have A. So you can add these two and write the answer. So you can write the final Q. What was the Q? This expression or this expression equals Q. Please fulfill this table. It is the important exercise. If anybody finish, please write down. I want to see how many of you done this truth table. Okay, as you can talk. What does it mean? We call line above the letters. Which line? This is just a table. There wasn't any B and C. Yes, the not means just to flip the numbers. For example, B is 1, 1, 0, 0, 1, and just like that. And there is also 1, 0, and also 0. And just write the C 1, 1. There is also 1, 1, and 0, 0, 0, also 0, and just OR them. Okay, let's see the answer. This is the answer. You can save that. You can take a photo, for example. So there is a Boolean expression and the other gates. We said that those true gates, basic gates, is OR and NOT gates. There are 3 basic gates, and you create all of circuits from these gates. So, but there is a different gates. For example, XOR, like F6. You have NOR also. It means not OR. And this symbol is like that. This symbol is like that. So why we need another gates? Because we have the basic gates, 3 basic gates, and we create all of circuits from that gates. So why we need the others? Because the feasibility and economy, they are economic than the circuits that create from the basic gates. It must be very huge, so you can want to use the other. You may want to use other gates. So the possibility of extending gates inputs, the basic properties of the binary operation, for example, commutative and associative, the ability of the gates to implement Boolean function, for example. So there was rules about that. For example, 2 are equals to constant f0 and f15s. Let's see that f0 is null, f15s is also identity, just binary 1. There are some same. So let's see the other logic gates. We know the AND gates and we know the truth table about that. So we know the OR gates. Also we know the truth tables of the OR gates. We know the inverter. It means not, right? It's unary. And we know also the truth table about the inverter. The complements, you can say inverter, you can say complements, you can say the NOT gates. So buffer means just connect, just like short circuits. So we have NAND. It is just like NOT AND. And there is a truth table about that. This is just opposite of the AND gates. And there is also NOR. This is also the opposite of the OR gates. There is also XOR. It's new. You have to memorize the XOR gates. If the inputs are same, like 0, 0, like 1, 1, it means the result is 0. If inputs are different, like 0, 1, like 1, 0, it means the output, the result is the 1. So it is just kind of compare the inputs, right? We compare that if they are equal or not equal. So just like that, there is a XNOR gates. It is the opposite of the XOR. So if the inputs are same, it means result is 1. If inputs are different, it means results are different. The results is 0. So you can use the multiple inputs like this example we did. There is a multiple input, right? There is not binary inputs. You use 3 inputs for 1 gates. You can use that. You can do that in the logic circuits. So you know these rules. This 2x expression is same, and all gates are commutative and associative. It means you can change the place. You can change the parentheses also. So let's see this one. What does it mean, this symbol from this table? It means NOR, right? These symbols are news for you. This means NOR, this means XOR. Okay. NOR means opposite of the OR. And you have this one, X, NOR, Y, the interconnection. This wire means X, NOR, Y, and you have also the Y, and the result is the same. This is kind of parenthesis. You can say that. You can switch the parentheses, replace them. It is means nothing for this expression. So multiple NOR equal A complement for OR gates. Multiple NAND equal A complement of AND gate. The cascade NAND operation equals sum of product. This means you can use 3 inputs and you can get this expression. Also, the NAND game is same. You can get this expression. So there is a cascade example. You did this. You know already. So there is a XOR X, Y, Z. You have 3 inputs. That means you have 8 variables, and there is a truth table about that. So, and there is a positive and negative logic. As you know, the 1 means high and 0 means low. You will see that all of the circuit equipments, especially in user guide, they use hash and L, high and low. They don't use 1 and 0, all of them. You have to know it means high. That means the component or circuit elements work with high. High means maybe 3 volts, maybe 5 volts. It is change from the situation. So there is also the gates with low and high digital gate program truth table. And there is a negative logic. It is not important. Negative logic, actually, I don't use a lot. This is just a general information. Okay. Today we discussed the Boolean function and corresponding truth table, and also we will solve the min term and max term. I want to show you a program. It names Logisim. Let's see I will share that. Let's see this example. There's a simple one, right? F2 equals x and not y and z. You can write this truth table, right? Please write this truth table for this expression, and we will work with some software, some programs. I want to see you. I want to show you. Can you see the logism? Okay. This program is very easy. You can see the gates in here. All of gates already in here, and you can put the gates like that and maybe erase them, and you can do some exercise with them. It's very simple program. Please learn how to use it. You can see the webinar videos from the internet or YouTube. You can watch them. Also, you can just learn with try, because as I said, it is very easy to use. And there is an input output block and gate block, and you can see you can create the logic one and you can simulate them. For example, with A1 it means equal 1. Please try to write the truth table and check if it's true or not, it is correct or not. So let's change them. It means also 1. And there is a 1 1 0 1 1. It means the results 0. So let's try this one. If this one is 1, and because there is a OR gates in the output, right? And in the OR gates, if any of them is 1, it means result is 1. In the AND gates, if any of them is 0, it means result is 0. In the AND gate, there is an interconnection, right? If we do the B1 and there is interconnection, that means the input of the AND gate is 0, C is 1, 0 1 means 0. So the result is 0. Please try to use this program. Its name's logism. So let's share another presentation. I'm uploading. You can see the PDF, right? Not logism. Okay, let's see. We will see applications of Boolean algebra, and we will see min term and max term. We will see what does means for the Boolean algebra. Oops, there's a mistake about that. There will be contents. So let's see. Nope. You cannot see that, right? Correct. I think you cannot see the PDF correctly. So let's do this. Let's try to share. You can see now, right? The paper. You can see the constant, I think. Okay. Okay. Let's see this paper. Conversion of English sentences to Boolean equation. We will see combinational logic design using truth tables. And we will see min term and max term expressions. And we will see what does this mean, min term or max term. And we will see example of truth tables and design of the binary adders and subtractors. This is our goal. We want to design adder and subtractors. So conversion of Boolean equation. F is true if A and B are both true. It means AND gate, right? If A and B equals 1, so F means 1. It says the true or false. We can say the 1 is true, 0 is false. So let's see that. There's an example. The alarm will ring. The ring means Z. If the alarm switch is turned on. Turned on means A. You have Z output and you have A one input. So the door is not closed mean B, or it is after 6 p.m. means C. Windows is not closed means D. Close means not close means you can say not D. So you have this equation, right? You have A if alarm switch turn on A and not B, or C and not D. This is your expression. And if you want to write the equation A and not B, or C and not D, and we can create this circuit, right? You can do that. So there is a truth table. Let's see the truth table. What does it mean? We have 3 inputs in this example. That means we have 8 variables. So there is a F, the result, and result is 0, 0, 0, and the other one is 1. The complement of F, it means not F, just flip the numbers. So we have this expression for F equal 1. What does it mean? There is F equal 1, right? What does it mean? It means A, not A, 0 is 0 means not, 1 is just equal to B, not A, B, C. Just like that. It means 1, right? So, another one. Another one is A, not B, not C. Just like that. We use OR gates. Because 1 or 1 or 1 or 1 or 1 equals 1. If any of them is 0, it means nothing for OR gates. One of them is 1, it means just the result is 1. So we have another one, A, not B, and C. So we have another one, A, B, not C. And we have last one, A, B, C. So this all of expression equals 1, right? This equals 1, this equals 1, this equals 1, this one, this one. Because let's see that not A equals 0, not A means 1. B equals 1, C equals 1. There is an AND gate in here, and all of variables is 1. Just like that. All of them is same. Just see that one. There is a like this. It's 1. Not B because B is 0. We have to get the not B, and it means 1. So C is 1. This is the one equation for the get 1. So there is also proof about that. You can write this equation like that. You can simplify it all of equation. We solve some proof. For this, I am saying again, you have to do a lot of exercises. Just use some books or use internet and do a lot of exercises for them. Because you can get this expression from this one. So the circuit realization is the simplest. Is the F. You can prove that with the truth table. Okay. Here is our function. This means F the 0, 1, A or B or C means 0. A or B and not C also means 0. A or not B or C means 0. We did in here 1 if when expression for F is 1, and we doing in here for 0 when expression for F equals 0. So that means we have this equation and we got this from this equation. So when expression not F equals 0, it's the same with that, like, right? F equals 0 means not F equals 1. This is the same equation. And take the complements of the F. This one and this one are complements of each other. Okay. So let's see min term and max term. First, we use 1, and in min terms we always use one equation. Max term we always use 0 equation. Let's see that. You will see that. Min term expression means standard sum of products. What does it mean? what is the sum of product? In the sum of product, you do just product the input. You use AND gates for products like multiplication, and take it like a variable and do the same all of them, and just sum the product. Sum means plus, so it means OR gates, right? Sum of the products, you first do the product, it means multiplication, it means AND gates, and you sum all of them. Just use the OR gates, just use the plus. So we use the sigma for the mean term expression. So these are those expression are same. F A B C equals sigma m m3 m4 m5 m6 m7. All of them was the one, right? Let's see that from truth table. 3, that was 0, 1, 2, 3 is 1, 4, 5, 6, and 7. All of them is 1, and we say that it is a mean term expansion. So there is a max term expansion. We use the 0 ones for max term, and max term means standard product of sum. Mean term was sum of product. We first product the inputs and sum the variables, and take it just like that components, and sum all of these components. In the product of sum, we first using the sum operation, then we get the variable, first variable, second one, third one, because we have 3 0 in the table, right? 0, 1, and 2. We have 3 0. So we have this sum and product the all of components. We have 3 components and we get the sum of them. So we use capital P for the max term expression. You have to know what does it mean. The capital P means the max term expansion, and sigma it means the summation. You can say summation or sigma. It means mean term. So we can say that there is a mean term 3 to 7, they are equals 1, and it means mean term. So we can complement the mean term also. The not f, it means 0, right? The complements. You can complement max term and mean terms. Mean term complements is max term. Max term complements is means mean term. So you can do the same thing with the max term. You can complement it, and so you got 3, 4, 5, 6, 7. Normally they are the mean term, right? They means they equals 1, but we got the complements of them. So we got this. So mean term and max term expression are complements each other, like we said. By using De Morgan theorems, you can get that. There's a mean term. There is also a max term. They are each other's complements, as I said. It's not a complex. Don't think complex. It's a very easy rule. You will see that. So, mean term expression for general function. This is a general function. This is a general truth table, right? There is a results. There is a inputs. You have 8 inputs. It's not changeable. And you have 8 results. It is not also a changeable. So, what is the mean term expression for general function? You can use this expression. Let's prove them. So, we said that f equals a0 m0 or a1 m1. So, continue like that. So, let's think about that. If a is 1, a0 is 1, it means mean term, right? So, we can put it 1 and we got m0. 1 is ineffective in the AND gate, right? 1 m0 is means m0. So if a1 is 0, for example, a1 is 0, you can write whatever you want. You can write 1 0 0 1, whatever you like. And let's say that a1 is 0. 0 is effective in the AND gate, right? That means if a1 is 0, m1 is not important. This one, this expression is 0. And we don't have to write 0 in the OR gates, because this expression is just this one. Nope, sorry. If a1 is 0, it means a1 and m1 means 0, and you don't have to write 0 in OR gates. So it is the same rule for max term expression. You can use the OR gates for this one, this function. Let's see if a0 is 1. It means 1 and or 1 or m0. That means this expression, this equation is equal 1, right? And you don't have to write 1 in the AND gates. So disappear this one, because in the max term we only use the zeros. Okay, let's see another part. All mean terms which are not present in F are present in not F. Just like say that they are each other complements. You can see from that not F 0 to 7 sigma, it means summation A, I and or MI complements. Those are the same rules. They are each other complements. So, what does it mean if we AND mean term and max term? For example, if I and j are different, so mi and mj, if different, it means 0, right? Because one of them is 1, one of them is 0. So there is a 0 in AND gates. It means it equals the 0. So let's see that there is a 2 mean term expression in here, and we AND them. So what will the results? F1 and F2, you can also get the same numbers. For example, the 0 is 1, the 0 is 1, so we get 0. There is a 2, but there is not a 2, so we cannot get the 2. There's a 3, there's a 3. Both of them is 1, so it means we can get the 3. We can get the 9, we can get the 11, not the other ones. This expression just explain these rules. This is kind of proof of this example. Just think the easy part and just take the same number if you add the midterm expansion. We will do a lot of exercises also in the lessons, and you will understand very well in these rules. Don't worry if you not understand now, because we will do a lot of exercise about them. That also means the same. So there is a not clear situation. You also will see that some of components, some of circuits, some of applications use not keys. So it means you can write in here 1 or 0. It is not important. If N1 output doesn't generate all possible combination of A, B, C, the output of N2 has not care values. So that means we don't know if input is 0, 0, and 1. If A equals 0, B equals 0, and C equals 0, what's the results? We don't know that. So we don't care that. We can use 1 or we can use 0. You can use whatever you want. So if not A, not B, not C, this one, we want to use the 0 assignments, we can say not A, not B, not C, like that. Not A, not B, not C means 1. Also not A, not B, not A, B, C. Let's see that. Not A, B, C equals also 1. So this expression means also 1. If we get the x 0, right? We can say the x is 0 and we got this expression for the 1. So we can take 1 the first x and 0 the second one, and we also get this expression because this one also means 1. It's different from this expression. It's just this one. And also we can say all of x is 1 and we get this expression. Okay, it is just a general information. You can see the x in the user guide or manual. It means don't care. You can took the results as 0 or you can took the results as 1. This depends you. So min-term expression for incompletely specified function, you can write in the min-term like this. Let's see the min-term again because I want to show you the truth table about that. So let's open to the min-term expression. Let's see the example. I want to show you the example about the min-term expression. Let's see that. Okay, I will try to share. Can you see that? Okay, let's share the just What about now? Can you see the logism? I think you're right. Yes, okay. This one is the mean term expression. Let's see like that. Can you see both of them? PDF and logism. Yep. Okay. Let's see that. We have 3 inputs, right? In the mean term expression, we said that we want to look at this truth table. In the mean term expression, we have this. And I create this one. Maybe, can you note this mean term expression, please? Please write the paper. And we will work on the logism. Please just write this expression. Or take a photo. And also take a photo this truth table. Okay, let's see that. We have 3 inputs, right? And we can change this one. It means 1, 0, 0 means 1. It is correct, right? From the truth table. 1, 1, 0 means 1. You can see the one with the green ones, green interconnection. And there is also 0, 1, 1, it means 1. And it means 0. It means also 0. You can show the truth table from this program. Please just work with this program and it will make you learn much more easy. Okay. Let's share. Okay, let's continue. And we were here, and there was a midterm explanation for incompletely specified function. If there is not care, you can put them like or, and in the max term, you can put them like and. So there's a XOR gate. Let's see the example of truth table construction for binary adders. Binary adder means sum, right? Adder means summation. So we have 2 inputs. It means we have 4 variables. Some of them, it means or we have 1, 0 plus 0 means 0. This is the decimal number. And there is a binary from this decimal. Let's see that there is a 0. Okay, there is a 0 and 0. This is a flag, some flag. There is a 1. Also, it means 0, 1. There is a 1 plus 0. It means 1 and it means 0, 1 in binary system. This is a binary system, as you know, and there is you can think that one is a decimal. Just 1 plus 1 equals 2. what does it mean to in binary? It means 1 0, right? Because 0 means 2 power of 0, it means 0, and 2 power of 1, it means 1. You have this one. So it's kind of like this. A, B are inputs, X and Y are outputs. We have X like output and we have Y. So it means the adder, it means the carry flag. We use the X carry flag and we use the Y just like a result. So 0 and 1 means 1, 1 and 0 means 1, 1 and 1, 0 and carry flag is 1, just like decimal. For example, if you sum 2 and 8, it means 0 and 1, it means 10, right? There was a carry flag. So there is a parallel adder. It is kind of important if we have a chance, get a chance to do the laboratory now. And if we will use the FPGA in lab, we will create the adders first. So if you get 1 bit adder like that, it is 1 bit adder, right? You have 2 inputs, both of them 1 bit, 1 output, it is Y, and 1 carry bit, it is X. And with using the 1 bit binary adders, you can create a 4 bit parallel adders like that. You have one full adder in here and you have carry in, you have 2 inputs, you have 1 output, and you have 1 carry output, and put those together and you will get the full adder. We will see the other weeks in this example. Don't worry, you will get it when you use the FPGA. It's just truth table about full adder. There is a X, Y, and also carry in. You have to get the carry in like a decimal number. It's just a summation. You add two numbers and get the results. You have carry and you have truth table about that. And you can write like that from the truth table. Sum and carry. You have sum X, Y, and carry in. You also have carry out, and with this one you can simplify with using rules and you can get this. I advise you to just memorize this one. The sum means XOR, and the carry out you use 3 AND gates like that, 3 AND, and put of them the OR gates. So you just saw the binary adder. Don't worry if you don't understand this example, because we will see that with very detailed. But you can think about that like a decimal number. So also you can have the subtractors with just flip one input, like A subtract B. It means if you can get not B, you can get the subtractor, not the adder. The opposite of adder means subtractors, right? You can get the subtractors just with using one NOT gate. We will do this example with Logisim next Monday. So let's finish the lesson in here. We will do the next lecture in Monday in the same hour. And we will do a lot of exercises about that. When we do exercise, you will learn better. I recommended you to please work with Logisim. Just try to do some exercise with Logisim. Thank you very much for these lessons and see you in the Monday, guys. Okay, take care.